Hello, hello. We should take this last hour to talk about the Numpy package with Python. And I believe I'm sharing my Numpy intro notebook. You'll have access to that again in the repository that we were looking at earlier, the intern Python training repository. So you should now have a clone on disk of that repository if you didn't already have a copy of it. So you can open it up and follow along. But for this particular notebook to work, you will need to have Numpy installed in your Conda environment where you're running the notebook. So if you will go through the process of doing the Conda activate, whatever environment is you have been using for this tutorial, and then Conda install Numpy from the Anaconda channel. The example that I'm providing here in the introduction provides the syntax for you, and you can see that if you just open up the non-interactive notebook in GitHub as well. So just clicking on the link will open up a version with all of the outputs there for you. So I'm just going to kind of push on through the examples and walk through this Numpy example notebook with y'all. Feel free to be putting other code in there, checking out how things work, looking for using the help or the question mark to see more about any of these specific methods. But Numpy is a pretty important package for us to cover because it does serve as the fundamental package for so many different scientific computing packages that we have for Python. And it's really going to give us another data structure through the Numpy array that will let us work really efficiently in Python with multi-dimensional gridded data. So perfect for meteorology type things. So this indie array object is just kind of like another collection, except it goes far beyond what we would have with a list or dictionary. And so it's a data structure that holds a bunch of data, large data for us, but it has a couple of requirements that are not imposed on lists and other data structures we've seen so far. The array objects are at a fixed size at their creation, so you can't expand them dynamically as you go, just adding on more and more rows. You can put multiple ones together, but in essence, like the original is the size that it's going to be, and then you can create others from that if you need to. And then all elements in the array must be of the same type. So maybe they're all integers, maybe they're all floats, maybe they're all strings. All are totally fine, but they all have to be the same type. And one awesome thing about Numpy arrays is they're pretty efficient. So they are fast because they are kind of optimized on the back end, hidden from our view, with pre-compiled C code, and that is providing some vectorization and optimizations that we just don't typically have if we're working on Python on the front end. So it's really connecting to the computer and understanding how the computer is most efficiently going to work with this larger data. Everything that you see here I grabbed from the What is NumPy section on the NumPy documentation, and then started following through some of the examples in the NumPy Quick Start. There are additional examples there that kind of mirror a lot of these, but I wanted to give you an interactive opportunity to see what's going on here. So the way that we use NumPy is to import it as a package, and here I'm using a syntax import NumPy as NP. You'll see this pretty regularly. Most of the common packages have a pretty standard way to abbreviate their package so that you don't have to go write NumPy every single time you want to use one of these options. You can totally just do import numpy and then type numpy where I've typed np. You don't have to name it np. You can name it whatever, but np is kind of the standard practice here. And so arrays are going to be very similar to our list object in a lot of different ways, but we have some pretty cool methods here, and I wanted to just start by creating an array whose contents are the indices of how they're numbered, and then reshape it. So I'm jumping right into creating kind of a complex set of methods strung along here, but this is really just to give us an array with some content so that we can start looking at different information about the array. There are tons of different ways to create arrays, and I've included a bunch of options here in the examples. But this one is creating a 3x5 array with 15 elements that will be numbered similar to our range command with the numbers 0 to 14. And so we're creating that as a 1D array, reshaping it as a 3x5 array. So we have 3 rows and 5 columns. And then the contents are going to be integers up to 15, but not including 15. If you have a NumPy array and you don't know much about it, maybe you've read in data to this array and you want to interrogate it, there are lots of different ways that you can do that. So here are a few helpful methods that allow you to describe an array, like its shape or the number of dimensions, its data type, or the type of array that it is. So this is just a couple of items here, just as examples of how you might interrogate your array. You can also create an array from a list. That's a pretty straightforward change here. So if I just have a list that I'm making all integers, I can totally just convert it to an array. And now I can do all of the array methods to that list. Note that you will need it to be an array to be able to call a lot of these methods. So you can't do this stuff to list, even though they behave somewhat similarly. You can do some cool things like setting an array to the size that you want it and filling it with zeros from the get-go. You can fill it with ones if you like. If you want to fill it with sevens, you can totally do that too. So you can multiply the whole thing element-wise by 7, and then all of your contents are there. Similarly for the zeros, if we wanted to initialize to 7s, we could just add 7, right? We get a 1D array from a range, like I kind of alluded to earlier. And that's going to be behaving similarly to our range command that we saw for lists. So we'll get a list from 1 to 10 if we provide it the arguments 1 to 11, because it's not inclusive on the end. We can also provide it with increments here that are less than 1. So this is not something that a list allowed us to do. So in this case, we will get the same range up to 11, but not inclusive, but incrementing by a fraction. So this is a helpful addition because not all of our real world problems are integers. And then kind of the flip to that is I know where, so with a range, I know where I want to start and I know where I want to end and I know the increment, but in some cases you might need to provide a certain number of points between two end values. So linspace is an additional item here that will allow you to do that. So say I want to go from 0 to 10, but I want 20 points along the way. I can use linspace to do that, and it takes care of the exact points that I need These will look kind of nicer, I think, if I stop with, nope, just kidding. So feel free to play around with what you get here, the values that come out of dividing these increments into 19 equally spaced increments, or 20. So I suggest here in the comments that you even try 2000 and then start to see what it looks like when you print a kind of large array. It's not going to print the whole thing for you here to the screen if it's pretty big. So you'll often see that it just provides you with the ... for the middle pieces, and it'll show you the first few and then the last few. I added a Numpy gotcha here. The A range that we were talking about up here is not inclusive. So if you do 1 to 11, you'll get 1 all the way up to the increment just before 11. But linspace is inclusive. So here I'm going from 0 to 10, and I want 20 items between those two. Then I will get both 0 and 10 as part of my resulting array. Okay, I charged in to some examples of what an array looks like, how to interrogate that, but I did that while we were still working on getting Numpy installed and spinning up a Jupyter notebook. I want to take a pause here to make sure that everybody's caught up with installing and running a notebook, and to take any questions that you might have about Numpy arrays in general.
I just had a quick question that I was downloading the Numpy, and then I copied the first line of code you did and put it into, actually I guess another Jupyter tab open. But when it says import NumPy as NP, it's telling me no module named NumPy, so just giving me like an error message.
Sure. So that is something that you'll see when you're working inside an environment or a space that doesn't have, has not completed the conda install NumPy step. So you do want to make sure that when you're installing, that you're installing in the same space that your Jupyter notebook is installed. And there's a potential that if you restart the kernel, if you think that you've done that, installed in the same environment, and you didn't get any errors, then you can try to restart your kernel, I think. So you can go to kernel and then restart and clear output potentially. And then click on restart and clear all outputs. And then give that another try and see if potentially that did the trick. And just as a reminder, I did set up a binder option for the GitHub repository. So if you do navigate to the GitHub repository and click that binder button, it will spin up a notebook that's mostly the same as this, with the NumPy installed, so that you can follow along with these examples. So I'm going to move on to NumPy operations here. And it's important to note that Python treats all of the mathematical operations as element-wise. That just means that if you have two matrices that are multiplied together, then it's going to multiply the first item in the matrix by the first item in the next matrix. And this is different than a lot of other languages, especially MATLAB. So MATLAB is going to, by default, perform matrix multiplication, and that's the whole, like, take the first row and the first column and multiply and add and all that fun stuff. But this is not going to do that. So all of your standard math operations are going to behave exactly like you would expect them to if you were working with just individual integers. So here I'm going to just create a couple of practice arrays from A range and ones and print them out here so that we know what we're looking at. And if I subtract these from each other, then we'll get exactly what we expect, 20 minus 3 and 30 minus 3 in each of the items that is returned from this function. We can also add and subtract, multiply a whole matrix by a single value. It doesn't have to be an integer, it can be a float. And it's going to, again, do element-wise math with that value. So remember, A was 20 here, we're subtracting 17 from each of the items in 20, 30, 40, 50. And here's the result. When you multiply two together, it's the same thing element-wise. You also have some math functions that are built in. You don't have to import math here to be able to use things like sine or cosine, tangent, arctangent, all that fun stuff. And then Numpy also has some constants that are built in. And here are a couple of popular ones, but there's a whole list here at the link that I shared in the comment. Sometimes you would potentially see that a value would be not a number, or it might go to infinity. You might need to represent that somehow. Or you might need to include pi in your calculation. So NumPy helps us out there. And then, of course, you can use all of the comparison operators that we've talked about. But when you do that with an array, you'll see that it will return an array of Boolean values for you. So again, just a reminder that A was set to all these values, 20 to 50. And then we're going to check any place where A is less than 35. So then it's going to evaluate each item element-wise and give you a Boolean value on whether that value was less than 25 in the original array. In some cases, you are going to want to do those matrix operations just like in MATLAB, and it's going to be a little bit of a different set of commands here than you would see normally. So to specify that you do actually want matrix multiplication, you would use the @ sign here. So if we had some ones and some other values, some indices values in another array, A and B, and then multiply those together matrix-wise, this would be the result. And then in meteorology, we often need a dot product for different calculations. So we have that as well. And the nomenclature here is a bit interesting. Dot is provided as a method to an instance of a NumPy array. So we can say original or first array dot the word dot, and then provide B, the second array that you want to provide the dot product of, as an argument to get the dot product of that matrix. And then we also have a couple of additional super helpful operators that are just going to act on the contents of a given array. So here I'm creating a randomized array. So yours will have different values in it, but I have all of these random values loaded in between 0 and 1. And if I want to add all of those values up in one easy to use method, I can totally do that. So this is going to go through and just add everything in there. We can find the mean of all these values. Max and min are similar. So you can really describe your array pretty easily. Remember that we have the ability to either tab and see all of the different potential methods that we could call and scroll through this little pop out here. Or we can always use our dir function on C, and again, see all of the different methods that we could call that don't have double underscores surrounding them. Google's also a helpful place to start with just how do I blank with NumPy. with NumPy. So anything that you might want to do to these matrix or array values, you could definitely find examples out there. NumPy is widely used. So another thing is that you don't have to take the sum or mean or whatever of the entire array. Maybe you only want to do it for columns in the array, or maybe only along the rows. And NumPy gives you the option to do that as well by providing an axis argument with the axis set here. So if you only want to find the minimum along a column up and down, you can do that with axis equals 0, and then it's going to return an array that provides the minimum value in each of the columns. So you'll have 5 values here because it's finding the minimum in each of the 5 columns. And similarly with rows, you would get 3 items back because it's going to find, in this case, the maximum of each of the 3 rows. I stumble with these concepts nearly every time I come back to NumPy, just so you know. So I will often do a whole lot of like, what size is this thing? How many numbers do I get back if I try to do it axis 0 or axis 1? Like, these are some of the cool parts of working in a Jupyter notebook so that you can easily interrogate the data, get a handle and a grasp of what you think you should be getting before you actually get the result and move forward with that. So just checking that things make sense along the way can help a lot. Unfortunately, I don't have a super easy way of having you remember these things other than play around with them. So there's a reference here. I am seeing a question. Is there a way to calculate a cross product using a method? Y'all are so much closer to the last math class that you took than me. Remind me, when we say cross product, do we mean the same thing as matrix multiplication? I'm seeing a nod. Okay, so yes, I'm pretty sure, like I was feeling that that was the thing, but yeah, matrix multiplication and cross products are similar. So you should be able to use the A at B, and then I'm looking quickly to see if there's another method instead of this like shortcut to use the at. So I'm just Googling, matrix multiplication NumPy, and totally coming up with matmul, because we can't write those things out all the way, all the time. Put it in the wrong spot. So if I did no. So this one's going to be a little bit different. It's going to be matmul, and then you'll provide it with A and then B. So you should be seeing the same thing that we saw up here. So that was a really nice question. There are cases where you might want to be calling a function instead of using a shorthand. And I will say that NumPy is pretty good about providing both. So if you want to be able to add to arrays together element-wise, for example, and use a function instead of the plus sign, there's typically a way to do that. And you don't see what I'm doing off camera here, but every time I'm answering these questions, I'm Googling. So again, add A to B will give you the same as just saying A plus B. So there are use cases where this could be handier than just saying A plus B. Thank you for providing a chat option. That there's also NP cross. This matrix multiply, which was literally the first hit on Google when I typed in matrix multiplication. But one cool thing about the NumPy documentation is that it will usually give you the section C also. So maybe this is getting close to the thing you want, but there are some other things that are sort of related. It'll give you those. And then it also gives you a whole set of linear algebra type things here. So there are a ton of different functions that you can use from linear algebra here, and start to get really deep into the math that you need to be doing. But there's also, like Taylor was mentioning, NP cross, and I haven't actually looked at that at all. Some things that you'll find, like here for Matt Mull, the way that I had to type that in was to provide the first matrix or the first array and the second array as arguments. And sometimes you'll find methods. So these are all functions that take your arrays as input to the function, but there are also methods. So let's see if maybe numpy.cross is a method instead. No, this one's still a function, and that's because you're going to call np.cross, provide it one array and then another. But you're getting all kinds of different mathematical functions this time when we looked at this. So you can totally just peruse here for the space for math. Okay. I've listed a whole 2 here, but we just saw me scroll through like 100. So a couple of built-in options work this way. You provide the NumPy function and then provide it with an array, and it spits out the exponent of each item in the array. You could do square root as well. There's a whole variety of different functions that I was just scrolling through here on the NumPy reference guide. Another thing that I get hung up with a lot, and I know other people struggle with, is indexing. Indexing can be difficult to keep track of. Here for NumPy, it's very similar to lists. So all of the examples I provide here, you will have already seen an example of in the list section that we did. So feel free to play around with what you might provide. This one's kind of a nifty one. You can reverse an array. So what this is saying is that we're going to do the start stop increment thing, but we're not providing any numerical input for the start or the stop, and we're incrementing -1. So it's just going to increment from -1 all the way around to the beginning. So it's a cool shorthand way to get a reversed array. And you can even change the values just like we did in lists, but you can change multiple values simultaneously. So this example would change every other value from 1 to 4, not inclusive, to 1000. So element 1, and then 3, but not 4 because it's not inclusive, or change to 1,000. And then of course you can iterate over arrays just like you can lists. So we're printing every item in the array and then subtracting 12 from it. I said that this can get a little confusing. NumPy arrays are very similar to lists, so you can kind of keep all those together in your mind moving forward. Things do get a little bit more complicated as we move toward packages that incorporate like X arrays, or pandas also gives me some trouble, and we'll talk about that tomorrow, but it's good to kind of keep these straight. And if you don't keep them straight, then it's good to have a Google nearby, which is my method most of the time. Questions, concerns about arrays and how to navigate them?
Could you go over the where you're putting the 1,000 in that array? I'm having a hard time understanding what the syntax for like the 142 is doing.
Gotcha. Yeah, I definitely skipped over that just a little bit here. So when you're indexing with these arrays, then you can put a start, stop, and increment separated by colons into the index part. So if we just took that out and said that I want to start at the first index and increment to the fourth index by 2, well, okay, let's start this again. Reset A here so that I don't just see the thousands that I plopped in there. So here, our first, let me do this. I'm sorry. Getting things all discombobulated here so that we can see what's going on. All right, so our original array had a bunch of cubes in it. And so if we wanted to reference the first one, the index 1, starting from 0, indexing again, and then go through the fourth one, so 0, 1, 2, 3, 4 through 64, but not inclusive, and increment by 2. So that's what these are: start, stop, and increment. So starting at 1, and then the next 2 down the list is 27. So I can reference it that way, but then what I'm doing in the next cell is reassigning those index values to 1,000. So we could go all the way to the end of the list. Actually, wait, what is the size of the list? So I don't mess this up. So if we wanted to say, what is the last item in the array? -1, just like a list. But if we wanted to go odd items all the way to the 10, can I do 10? No, I think I have to do 9. By 3s. So we would be picking out every third item in the array. I can do 10 there. And that's another thing. I'm like, wait, can I reference the 10th item as the 9th index? You can't. Did I?
That makes sense. Thank you.
I was gonna ask, did I clarify anything there or just ramble on and stuff? Okay.
Yeah, so it's then that makes sense then how that one the revert how you reverse the array works. So like if you wanted to do like every second element of the entire array, you could just do : 2.
That's right.
Okay, cool.
That is totally right.
Yeah, I get it.
So this is essentially just leaving out the information about the start and stop. And so it's going to default to the 0 and last item, and then just do every other one. Great questions. Not hearing any other questions, but I definitely invite them if you have them. This is getting to be the tougher side of things to understand with Python. And it gets a little bit more complicated as we go. Okay, so multi-dimensional arrays are probably going to start getting into that space of what's going on here. I mean, for me, that's definitely the case. Like, again, this is the space where I am constantly trying to remind myself, like, how do I make these references? Let me do a little sample to check what's going on. I was doing this the entire time I was preparing this notebook. So please understand that this is not something that's just obvious to folks or something that you just remember forever once you hear it once. For multi-dimensional arrays, this just means that you would have kind of a list of lists, or you can think about having a grid on the globe of latitudes and longitudes and that sort of thing. So at every point on the globe, you would have maybe a temperature value saved in this array, just as an example. So here I'm going to start talking about two-dimensional arrays, and these can get larger. If they're getting much larger than 2 or 3-dimensional arrays, you might want to consider moving toward X-array instead of Numpy as your package and data manager. It's going to be built on Numpy, like I mentioned before, as the fundamental basics, but it gives you a few more tools to manage those larger data sets. But we will talk about 2D multi-dimensional arrays here. But here's one more example of how to create an array from scratch. Most of your arrays are going to come from a data file that you're going to load in, most likely. But I thought I'd throw in a variety of options. This is another place where, excuse me, a lambda function might come in handy. I just put a function in here, named it f, but you could totally replace this with your whole lambda. If I could ever spell lambda correctly, and then it returns this value. So this is just an alternate syntax for the same exact thing, I hope. But it's just going to essentially fill my array with some function that I defined here with 2 arguments. So here I'm just adding together the square of x and the square of y. So we'll see that we get a 6x3 array here. So 6 rows and 3 columns. So this is going to be row column order. This may trigger something if you've learned another programming language that was C-like or Fortran. Those are 2 opposites. Some languages do column first ordering here. We're doing row first ordering here. So 6 rows, 3 columns. And if we want to reference any single one of these items in our multi-dimensional array, we can do that using a comma separated list inside our square brackets as we're indexing. So if we look at the 4th row, 0, 1, 2, 3, 4, and the 2nd column, 0, 1, 2, we would expect that this would give us the number 20 back. And it does, so that's great. You can also do whole chunks at a time using those colons again. That just means everything in this column or row I want to see, but I only want it at one of these points. So to see the entire last column, we could put -1 here and give us every row in the last column is what this is saying. So then we're seeing, just as we expected, that we get 4, 5, 8, 13, and so on to get all of those. If we wanted to switch that up and do all of the rows in the first column, column 1, we can do that as well. And so we would get, did I say that backwards? My apologies if I did. But we're getting the first row in every column in the first row. So we get 1, 2, and 5. Sometimes we may be interested in masking out values that meet a given criteria, and that's something that we use pretty commonly in meteorology. So here we have the NumPy where function that will allow us to do that. So I can say where my array is larger than 12, do return the value of b, and otherwise fill in a not a number. So this is just like our conditional. If we were to do an if statement, it would be if b is greater than 12, then return b, otherwise return none. And I'm going to go ahead and run this so you see what happens here. It just fills in the non-value in all of the places where our condition is not met, and then returns values where it is met. Let's see, a question in Jamboard. If we have multiple levels and want to reference a specific row, column, and matrix, can we do B322, for example? I believe you can. So what if we added a dimension here? I'm totally going off script, so it's probably gonna like blow up in my face at some point, but let's try it out. There we go. So what was happening here is that I'm going to have 3 values as we're going through this 3-dimensional array. So as you add dimensions to your arrays, you would need an additional value here in your lambda function for this particular thing that I decided to create this this array from. But yeah, then indexing this array, you could do like 1 everything and 2. So it's just, and then it's telling me that I'm out of bounds because the third dimension is only size 2, so I can't reference 2, 0, and 1 are my only options. So then it gives me 2, 3, and 6. So this is saying that we're going to do all of the columns in the first grouping here and in the first column. So 2, 3, and 6. And this is definitely one of the spaces where I have to really start playing with exactly how these numbers are ordered and what we're referring to. So creating a toy like this to really nail down how your indices are used is pretty important. All right, I saw the post-it magically moved down to the answered pile, so I will move forward. All right. So then you can do this one other way as well. Like if you wanted to assign all of the locate. Oh, these are all going to fail now. I'm going to have to go back and make sure that I have my original definition of this for my original examples to work. Apologies. That one's going to fail. That's fine. So we can also work with reassigning values and applying masks in this way as well. So this is going to say wherever B meets the criteria that B is less than or equal to 12, then set that value to 0. I was running into some issues when I was testing this yesterday. If I tried to do not a number here, it would complain. And that's just because it can't convert not a number to an integer value. So you do get that additional perk of using the actual where method or function, apologies, with the whole idea of being able to manage your data types. Because when we returned this new value, we returned a whole new array, and that array could be defined by the not a number being a float. So it was able to deal with that a little nicer for us. But since B was already an integer array, if we look up here, we defined it as an integer array. To do it in place, we would need to set it, the mask, to an integer value. So I'm just choosing 1 here, and that totally works. So you may run into that type issue when you're doing this in place. And then we can definitely iterate through every item in the list. We can do it with nested loops if we wanted to, or we can flatten the whole array and do it one item at a time in a 1D array. So we get the same kind of thing. Here I'm just doing it. When I print it, I use the space instead of the new line. But I want to caution you against any situation, unless it's absolutely necessary, for looping over items in an array when you're doing some kind of calculation. Try to do something with methods that will do the same calculation for you. What I found is that there is nearly always a method that'll handle it for you. And when you do it that way, you're taking advantage of that vectorization that has happened in the background that we don't ever have to think about, and it's much faster. If you iterate over every item, it's going to slow your program down significantly. And it's also kind of a fun trick to figure out how to get that speed up. The only time that I've really needed to iterate over every level or something was when I was doing like something vertically in the atmosphere. A lot of times we need to know like the value at the next level so that we can compute like the mean or the layer thickness or something like that. And when you need the next value, you're often going to need to be iterating and saving values from the one below it and that sort of thing. So that's really the only situation that I found that really requires a loop. So know that you can loop, but try real hard not to. If you have more questions about that when specific things come up, I'm always interested in helping figure out how to get around that loop. So let me know. Okay, 2 other topics here just quickly. Oftentimes you'll get a couple different arrays from different locations and they're saved with an odd shape or the wrong shape for being able to put 2 data sets together or something like that. So you have a couple of options for redefining the shape of your data. Ravel is going to flatten everything out into a 1D array for you. So here again, we're just creating a random array, Ravel then is going to flatten this out. So instead of having these two stacked on each other, they are now part of one array. So this was the first and this was the second, as we saw it here. As long as you have the right number of elements, so I have 2 times 6 elements, 12 in my original array, I can reshape it into anything that has 12 elements. So 3 by 4 works. So here again, we are taking the first 3 items and putting them in the first row, and then the next 4 items and putting them in the second row, and so forth. So that's what reshape is going to do. And then transpose is going to switch the rows and columns. So where we had 2 longer lists, now we have 6 of those. So shape is going to probably come up in your life at least once this summer if you're working with Python and data from various sources. So know that these are options there. And then sometimes you're going to want to stack multiple arrays together, and you have a couple of options here as well. So know that when you're putting these together, you can do them horizontally or vertically. So horizontal stack and vertical stack will kind of glue these things end to end or on top of each other. If you have arrays that are larger or higher dimensions, then you can use the concatenate. And you are going to need to make sure that the axis that you're concatenating on is appropriate for the squeezing together. Like you couldn't squeeze together like something with the dimension of 3 and something with the dimension of 2, but perhaps you can have an index here that will help get you to the right shape for the thing that you want to concatenate. You can also specify which axis you'd like to concatenate on. So in this case, the last element of C was appropriate to be able to concatenate with A because it was a 2 by 2 from way up here. So I was just able to put those two together. And it defaults to the 0 axis, so they're stacked on top of each other. And if I want to try along different axes, I can totally do that and kind of see what shapes you get out of choosing different concatenation axes here for two different arrays that are the same shape. So just a little thing to play with and see what you get. Whew. Y'all, that's a lot even for an intro. I got through it, but now I'm happy to answer any questions as always.